Hello everyone. Today I'm going to discuss the speed of sound. I'm going to derive a formula for speed of sound in air medium. So the speed of sound in air medium is given by V equals under root B by rho, where B is the bulk modulus of the air medium and bulk modulus B equals minus delta P divided by fractional change in volume. Okay, delta P represent change in pressure and delta V by V represent the fractional change in volume, and rho is the density. Okay, rho is the density of air or the medium in which sound is propagating. Now let us consider a long air filled tube. Okay, we are taking a tube filled with air, and we know as sound propagates through the medium, the particle of the medium undergoes compression and rarefaction. Okay, so let us consider a compressed region. Okay, this is a compressed region, or let us call it pulse. Okay, and this is an uncompressed region, or this is undisturbed air. Okay, this is un so let me write over here. This is undisturbed air. Clear? Now let P be the pressure of undisturbed air and V be the speed of this region. Okay. Now we always know in case of compression, okay, the pressure is high. So let P plus delta P be the pressure of the compressed region, and delta P is taken positive for compression, and definitely the particle or air inside the compressed region will have lesser speed. So let V plus delta V be the speed inside the pulse. Okay, and delta V is taken negative. Now we choose a reference frame in such a way that the pulse is at rest. Okay, now let me draw the tube. Okay, so this is actually the same tube. So for convenience, I'm taking this tube, okay, to show exactly how the air molecules or the air particles are moving. Okay, so this is a pulse. Now let us take a moving fluid element of small thickness, okay, delta x. So we know the air particles or particle of this region, they move, okay, more freely in comparison to the particle of this region. So we are taking a moving fluid element. Okay, so this is a moving fluid element, and let V be the speed of this element. Okay, and A be the area of cross section. Okay, so we are taking a moving fluid element which is moving with the speed V towards the pulse. Now this element strikes the pulse. Okay, so I'm drawing a tube. Okay, so this is the same tube. Okay, so now what happens? The element, okay, strikes the pulse. So this is a pulse. Okay, this is a pulse or a compressed region. Now this side of the element is called trailing phase, okay, and this side of the element or moving fluid is called leading phase, okay. The leading phase is in contact with the pulse, whereas the trailing phase is away from the pulse. Now slowly the element enters inside the pulse, okay. As the element enter inside the pulse, it get slowed down, okay. There will be slowing of the element, and the slowing continues until the element is completely inside the pulse, okay. That is until the rear phase, okay. This is the rear phase, rear phase of the element is completely inside the pulse. So we can, let me draw a tube, okay. So I said earlier, the slowing is completed until the element is completely inside the pulse. Clear? So the slowing is completed until the element is completely inside the pulse. So the time for slowing, we need to find the time for slowing, okay. So let me write over here. We know simply speed equals distance by time. So since we are taking element of thickness delta x, so the time for slowing is delta t, okay. Let us take delta t as the time for slowing. So delta t equals distance is delta x divided by v. So let us call this as equation 1, okay. Now let me erase this figure, okay. So let us come back to this figure. Now if you see in this figure, okay, as I said earlier, this is a trailing phase or the rear phase, and this is the leading phase. So let us find the pressure or the force on leading and trailing phase. We know pressure in this region is P, and we know pressure P equals force by area. So force on trailing phase is, okay, so force on trailing phase is PA. So this is force, okay. This is force on trailing phase, okay. This is P times A. Now force on leading phase, okay, force on leading phase equals, we know pressure in this region is P plus delta P, okay. So let me erase this. P plus delta P times A. Now we have to find the net force, okay. So the net force, so let me write over here. net force or the average force, okay, during time interval delta t. So I'm writing in short, net force equals pa minus p plus delta p times a. We can subtract force on leading phase minus force on trailing phase, or force on trailing phase minus force on leading phase. Okay, so we get net force equals pa minus delta p times a. So pa and this minus pa, it cancels, so we get net force, and let us call net force as F, equals minus a into delta p, or a times delta p. And what does this negative sign imply or mean? Negative sign indicates that the net force is towards left. Okay, the element is moving towards right, and the net force is directed towards left. So negative sign indicates that the net force is directed towards left. So I'm writing in short, this is towards left. Okay, now we know force equals mass time acceleration. Okay, so we use Newton's law. So let me erase this. Now let us take mass of this element, okay, as delta m. Clear? Because we know force equals mass times acceleration. Okay, so let us take mass of this fluid element as delta m, and let delta a be the acceleration during time interval delta t. Okay, so we are finding net force during the time interval delta t. So this is net force. Now let me erase this also. Okay, we know density, because we want final relation in term of density. So density equals mass divided by volume. So delta m, that is mass, equals density into volume, and volume equals area. Okay, area of cross section times the thickness. So we get force equals delta m is rho a delta x. Clear? Now what about acceleration? So let me write over here. Acceleration delta a equals delta v. This is small v. Okay, keep in mind small v for speed and capital V for volume, divided by delta t. So we can write delta a as delta v divided by delta t. Now we can simplify this expression further. So we can write F equals rho a, and delta x is v times delta t, and we have delta v by delta t. Okay, so let me keep this in a bracket. Now we can equate this force with this. Okay, so let me erase this. So we can write, if we equate this to relation, okay, we can write minus a delta p equals rho a v delta t delta Vy, delta T, okay. Now let us cancel A, okay, and delta T, okay, cancels out. So let me erase this. Now we can write delta P equals, so we have negative sign, okay, here, minus delta P equals rho V delta V, okay. Now let us apply a trick, okay. So I'm writing rho, so let me write in this way first. So I'm dividing by V, so I need to put V, okay, on the numerator, okay, on this side, so that we have V square, okay. Now rho V square equals minus delta P divided by fractional change in speed, okay. This is fractional change in speed. So what we want this, okay, B equals minus delta P divided by fractional change in volume. So we have to change fractional change in speed to fractional change in volume. So let us change the fractional change in speed to fractional change in volume, okay. So for this, what we do, so as I said earlier, we have to change this, okay, change in speed by original speed to change in volume divided by original volume, okay. So let us do some rough work. Now V is the volume of the element. As I said earlier, V is the volume of the element, and volume of the element is A times delta X. And we know from relation 1, or we have derived delta T equals, because we have this, okay, speed equals delta X by delta T. So delta T equals delta X by V. So we can simply write volume V, volume of the element, before entering the pulse, okay. So this is delta X is V times delta T. So we have V equals A V, this is speed, times time interval delta T. Now as the pulse, element enters the pulse, the element get compressed. So there is change in volume of the element as it enters the pulse. So we need to find change in volume, okay. So the change in volume of element as it enters the pulse is delta V, okay. This is A, and we write change in speed, okay. You can see A is actually constant and we have time interval delta T. So change in volume is associated with change in speed. So delta V, okay, small v, times delta T. So we have these two relation. Now let us divide delta V, that is change in volume, by original volume. So we get A delta V, that is change in speed, times time interval divided by A original speed, and we have time interval delta T. Now let us cancel A, okay, and delta T also cancels. So we get, okay, change in volume to original volume equals change in speed to original speed. So we can write, okay, rho v square equals minus delta p divided by fractional change in volume. Okay, now this ratio, okay, is the bulk modulus. So we can also write bulk modulus B equals stress by strain. Okay, so let me erase this. Okay, okay, from this, okay, rho v square equals B. So we can write v square equals B by rho. So speed v equals under root B by rho. So this is the final expression, okay, which gives the speed of sound in air medium. So only this much for today. Thank you.